just the low level features are identified during the initial period of training, and finally when the high level training is acquired, you can see that the entire facial features are extracted at the towards the end of the process. Now when it comes to deep learning, all might have heard that deep learning is a subset of machine learning, and it imitates the way humans gain certain types of knowledge, or we have heard that it imitates the way how human brains work. Is there anyone who have not heard of it? We might have heard that okay, there are neurons there in our deep neural network, and neurons are like the neurons in our brain. Something of that sort you all might have heard. There might be people who already know well that I'm not talking about them, but if people are new to deep learning, anyone is there, you might have at least heard that deep neural network is something that is similar to how human brain functions. Is that right? Okay. So you can see an image there, and I have to acknowledge that I have taken some content from the course Intro to Deep Learning by Mitesh Khapra that is provided under SWAYAM course. Maybe that most of you might have done. I'm not sure if anybody has done it. If so, you might see some repetitive content, because I have felt it was a very amazing course for anyone to start with deep learning. So some content I've taken from that. So he has prepared the PPTs in such a way that it was very easy for anyone to understand. So what this particular image, it's taken from his lecture. So this is the representation of a biological neuron. You can see there. I'm not an expert in explaining all those concepts, but at least you can take into consideration those neuron part, which is actually called soma here. And we have the axon and synapse, which is the connectors. Okay, so here dendrite is the connector, or the what do you call it, edges. You can relate it with the neural network edges that receive signal from other neurons. Synapse is the point of connection to other neurons. Neurons are getting connected. Neurons among themselves are getting connected using synapse, and axon is the responsible part that will transmit the output of this neuron to the brain, or you can say that is the point of that is a place where the trigger happens when some visual instinct is found, or when something funny is found out. The brain has to be given an information. Brain has to be triggered that something funny has happened and a person has to laugh or not. So that kind of information is transmitted using axon. So we'll just try to relate it with the concept of neural network. So what I'm trying to cover is what exactly is a neural network, what all kinds of neural networks are there on a surface level. Within 2 hours, that is what we can hardly cover. So what is a neural network? What is the fundamental principle behind a neural network? What backpropagation is, forward propagation, what activation functions, loss functions, some basic terminology related to neural network will be covered. Then some specialized neural networks like CNN, RNN, as given in the schedule, convolution neural network, recurrent neural network. These will be also basic concepts. The surface level concepts will be covered. Okay, so before moving into the actual neural network, we should understand what it is, how it is functioning. So that is what is being compared with the human brain. You can see a funny illustration there. It's actually part of a Big Bang Theory series. So at least a few of you, if you've known, you can relate that scene. But then that is not what is important here. What we're trying to say is, when you find a funny visual or a video, some people might laugh when the visual is funny, or some people might the funny part of your brain might be triggered when the speech style is funny. For some other people, it might trigger when the text is funny. Whatever is shown as textual representation is funny, some people might find that funny. So there might be a rule in your brain. Just imagine that there is a rule in your brain that you have to, or that funny or hilarious part of your brain has to get triggered when at least 2 of these 3 inputs is fired, or if it is triggered. So if at least visual and the speech is funny, your brain is going to tell that it is hilarious and you can laugh. Or if speech and text is funny, your brain is going to get triggered and you're going to laugh. Or if visual and text is funny, then also the same. But there might be scenarios where just one is funny, like visual alone is funny. So then in that case, your brain is not triggered, or it doesn't classify that the input is hilarious, and you are not going to give a laugh. Okay, so that is how the brain functions. In the same way, you have the apparently the actual neural network looks like this. You have an input layer where x1, x2, x3 to xm. This can be related to the inputs here, visual, text, and style. If any of these inputs are uh, on, or if it is true here, if in the actual scenario it's not just true or false, you can take any number of values, but I'm just relating it with the previous ones. If these any of these are triggered according to the weights that are given to this neural network, according to the edges that it transmit through. One second. Based on the edges that it transmits through, maybe in the output layer you might get an indication that something has happened and it has to be triggered. There might be rules or the patterns might be learned by this neural network, which will lead to a particular trigger in any of the neuron of the output layer. Okay, this is how it is related to the actual brain. Did you get a basic idea? I mean, I have not started off with the actual neural network, but I'm just asking you whether you could relate it with the functioning of a brain. At least this part, like if any two of this is fired, then the output will be fired. That is what the connection has to be understood. Like when is the output triggered? Here also, when is the output triggered? It's based on the input values itself. At least that much you have to understand. Okay, I can see a few yes. So I'm moving ahead. This is the basic structure of a neural network. We'll start with the actual technical aspect. We are leaving behind the biology part, which actually I'm not that expert about, but I just took this illustration for us to relate. So this is actually a neural network. You can see that there is an input layer, and the dimension of this input layer is going to be the dimension of your data set. Dimension in the sense, suppose you have a data set with 6 features, which means you'll be having 6 columns, right? 1, 2, 3, 4, 5, 6. 6 columns will be there, but maybe lakhs of records will be there. Lakhs of records will be there. So the input layer will be having 6 neurons. 6 is the dimension or the size of your input. So one input means it's just one row. One row will be having 6 values. So your input layer dimension will be of the value 6. Then you have a set of hidden layers. At least one hidden layer should be there for a neural network. One hidden layer should be there. Then only it becomes a neural network. Otherwise, it is not a neural network. You should have one input layer, one output layer, and one hidden layer at least. At least one hidden layer. Here I have demonstrated with 2 hidden layers, but at least one hidden layer should be there. And every nodes, every neurons are connected to each other. You can see that there are exceptional cases, but we are not learning the complex possibilities. As of now, we are learning the basics. So you just keep in mind that all the edges, all the neurons are connected to each other. You can see that H3 is connected to all the output neurons, or you can take X3. X3 is connected to all the hidden layer neurons. All the connections are established. Now, okay, 2 other important things. Just let me erase whatever is there. Now, 2 more important concepts that you have to understand here is during a deep learning training, during the training of a deep learning model, you have a forward pass. You have a forward pass where you have the input values. You multiply it with the. I hope you have heard that during on these edges you do have some weight values. You have some weights allotted to these edges. Based on that weights, it is what triggers your model to bring out where it has to be mapped to the output layer. Okay, you have weights associated with each of these edges. So based on the weights learned is how your model is going to function. So during the forward propagation, what happens is we start the process by initializing a set of weights for each of these sets of edges. You have a lot of edges here, right? From H1, you can see that there are connections to all the output layers. From H2 to all the output layers. So for each of the edges, we have weight values associated with it. Initially, it is randomly initiated for the first iteration. So there is a forward pass with the random weight values that is assigned. There is a forward pass with the random weight values assigned by multiplying x with the weight value x1 into w1, x1 into w2 plus. So you have a combination of computation that is done here, which we'll see in the next slide. The actual computation I'll show you in the next slide. So there is a forward pass. Before that, just understand this terminology. There is a forward pass wherein the computations are done based on the initial weight value, and you associate the computation with the output layer. Once the output layer, output values are computed, you do have the ground truth values as well. What is the ground truth? We started this process since we had a data set, right? We already had a data set where you have X values and you have the Y values. So already a set of Y values are there, which is the ground truth, which is the collected Y values. Here, the y values represented is during the forward pass, you get a set of y values based on the computation. This set of computed y values is compared with the ground truth y values for evaluation. Probably yesterday, Disha ma'am might have taken the evaluation part. I think evaluation metrics is covered, right? How do you evaluate a model, be it ML model or deep learning model? We do have a certain set of output that is computed by the model. We do have a ground truth set of values which we already have. We set aside a test data set and we compare the computed value with the ground truth value. So the same thing is happening here. During the forward pass, you get a set of y values. You already have a ground truth set of y values. We compare these two. We compare these two whether the predictions or the outputs that we got now is comparatively closer to the ground truth values. If not, there is a computation that has to be performed there to check that. Uh, Probably the difference values, right? Y1 minus the actual y1 whole square because of the negation sign. So some computation is performed. Just imagine some computation is performed to compute a loss value. If that loss value is not acceptable, we try to update the weight values by going back. Update the weight values by going back. That process is called back propagation. So we have a forward pass. We also have a backward pass, or which is called the back propagation. Back propagation is a very important step in deep learning. It doesn't come in machine learning. We do have weight updates and all, but we don't call it back propagation. But in deep learning, we do have this process of back propagation, wherein we have the forward pass. We find out the loss value. If the loss value is not minimal until now, we go back. We back propagate by updating each of the weight values, and then we again do the forward pass, again compute the loss, and this training goes on until you find out the minimal loss value. That minimal loss value, I think I'll show the gradient descent. That's what I'm searching for. One second, I'll just show that image and we'll come back. Yeah. So we'll be updating the weight values, again computing the loss. Each time the loss is computed with a new set of weight values, we are aiming for the minimal loss to come up. Okay, so once we arrive at the minimal loss value due to a combination of weights, those weights values will be considered as the actual model. So when you're talking about model, after training you get a model. What is there in the model? What are you expecting the model to be? Slow down explanation. Yeah, obviously I'll slow down. I thought I was a bit slow actually. I was moving on a bit faster. I was trying to move, but actually I've not started with any technical aspects. It's just a surface level I'm discussing. Maybe I'll go through it once again. Is that fine, ma'am?
It's okay, ma'am. We are
Yeah.
able to understand. Just if you
It's
could
actually,
reduce
it's
the
actually
speed of explanation. That's it.
okay, ma'am. It's actually a shift from the machine learning models to deep learning model, quite a bit more complex if you're listening it for the first time. But
Thank
maybe over the period of time, when you listen to it for more than one or two times, it will be clear.
Yes, ma'am. Thank you.
Okay. So what we are aiming is to find out the minimal loss value with which you will get a set of weights and bias which will be saved as the model. So whenever we tell that after training we are saving a model, we always speak of model, right? What is stored in that model? Any idea? What is part of that model? It's applicable to machine learning also. When you talk about linear regression, what is actually saved at the end after training or after fitting your data into the model? We talk about some coefficients, right? Weights and bias. We do have, yeah, learned algorithm. Learned algorithm, fine. What is being learned? The parameters are being learned, right? The best weight values. That is exactly what is stored in the model. So when you speak of a file name called model, once you train a deep learning model, you will get a file called maybe H5, or some people save it as serialized file. So that file contains a set of weights and bias values. That is one important thing that you have to keep in mind, weights and bias. So this can be of any precision. Accordingly, the size of that file will vary. And it's not just weights and bias, it is a bias which is stored. The architecture of the model and the optimization algorithm that we have used, all these things are also stored as part of this model file. Okay. So I just showed this image just to tell you that we are aiming for the minimal loss value. And the gradient descent algorithm, I think yesterday ma'am has described is what she told. So I'm not explicitly telling what it is, but you can understand from this image that for every weight combination, suppose you have just two weights. In the real world scenario, the number of weights that you're going to have is huge. As I showed in the network there, you had large number of weights. So for every weight combination, you will be plotting the loss after every forward pass. This is the loss indicator. Okay, we'll be plotting the loss, and we are expecting that the loss is going to get reduced to a particular point, after which it is going to get increased. So we are going to find out the minimal value. That is what we are interested in. That is why we are training the model for. Okay, we'll just come back and start once again. Okay. So this was our neural network. As I said, we have a forward pass wherein we perform the multiplication and addition of input neurons and the weights. And at every hidden layer, we have another set of computation. We'll come back to that. And once you reach the output layer, we have a loss computation. We back propagate the error, update the weights with the gradient. There is something called gradient. Again, we'll see that all in the upcoming slides. So these are the main things that you have to, and from this slide, what you have to take away is the input layer, you have an output layer, you have hidden layers. It is represented using H1, H2. Input layer is represented using X1, X2, and the output layer is represented as the Y values. So when you have multiple Y values, it means that it is a multi-class classification problem. Then you should understand what is forward pass and backward pass. Until that, if you can get from this image, we'll move ahead and see the remaining concepts. Although in between I spoke of what weights, multiplication, addition, back propagation, gradient descent and all. We'll see that again in the upcoming slides. Okay, you can skip that slide. So basically, in this is the entire neural network. I'm just taking one portion of this and it is explained here. So with this, you might get a more better picture. Okay, so what happens at a single neuron? We are going to talk about what happens at a single neuron. Okay, I hope you have understood that each of this is a neuron. Each of this is a neuron. So what exactly happens in a single neuron is, neuron is also called a perceptron. It's a single perceptron. Actually, two kinds of functionalities happen there. Two kinds of functionalities are computed there. One is summation. Summation, as I told, the input values are connected to these neuron using many edges. Each of these edges has some weight values, theta 0, theta 1, theta 2, and theta m. So when you multiply it, what are you going to get? X1 theta 1 plus X2 theta 2 plus Xm. I mean, you have many inputs, so dotted Xm theta m. That is going to be the summation that is going to happen here. And you have an additional value that you can see here. You might get different kind of representation for this particular aspect. This is nothing but the bias. When you learn the linear regression, when you want to represent a straight line, you have a equation of the form Wx plus b. Wx plus b. Or if you have multiple variables, it's going to be W1 x1 plus W2 x2 and so on. You have multiple variables there. So this B is nothing but, you can also represent it as W0, right? There is no mistake in representing it as W0, which means that you're multiplying it with 1. So in place of X, here you are going to have the value 1. The same thing is represented here. Instead of X, you have a value 1 here. Theta 0 is represented here. So you get a generalized representation. You have a bias value, you have multiple input and the weight values corresponding to those inputs. Initial weight values, those are random values. And you are feeding it into the perceptron. So perceptron, both of this combination is actually a single perceptron. It's not just a summation alone. We do have a nonlinear function associated with the perceptron. I'll tell you why this is required. If you just have the summation, what happens is every time you can end up with only linearly separable data. Okay, you can only create a model that is linearly separable. But when we deal with real world data, it's not that data is always linearly separable, right? You do have nonlinear separations required as well. In certain scenarios like this here, if you're trying to separate these data points into red and green, you can never have a straight line that would separate the red and green lines. So you should require some nonlinearity here, bring out some nonlinear representations, but that would clearly split out the data in its proper format. So for introducing nonlinearity, we do have something called activation functions. Activation functions. Okay. So it's not just summation. Summation along with this activation function will give you the output. That is how we are computing the output for every neuron in the neural network. So it's not just the case of output. In between every hidden layer goes through the same process. So for this neuron, if you're taking, you will have x1 w1 plus x1 w1 plus x1 w1 plus x2 w2 x3 w3. That will be the sum that comes up during the half of the neuron, and the second half is for introducing the non-linearity. So both the process will be represented in that neuron. So the same way, we are just taking off one neuron and we are explaining it. You have all the inputs here, you have the weights associated on the edges. You are first summing it off. Summing it off means it will be a linear representation. Obviously, you know that w1 x1 plus w2 x2, that kind of a representation, polynomial equation will always end up with a straight line or a hyperplane. It's not a curve anyway. So that linearity has to be changed to non-linearity by applying a non-linear activation function. So these are the main steps included while you're computing the functionality of a perceptron. It starts with inputs. You have a set of weights. You perform summation of it. Then you introduce non-linearity, which will lead to the output. These are the main terms associated when you take a single neuron. Okay. You can have a technical or mathematical representation of that in this form, wherein here you can see theta 0 plus x transpose theta. What that means is theta 0 is the bias value, as I told earlier. You can, in some representation, you can see this as a single term, x transpose theta alone, wherein x will take value from 0. Here x is taking value only from 1. So theta 0 plus x transpose theta, x transpose, why we have indicated it as is because you can show your input values as metrics. My screen has got a problem. I cannot write on it. I'll just show you one. Try to take a blank screen and show. So you could see there that it was x transpose theta. Why is it represented in that way? Is that what we are expecting is we need to have x1 theta 1 plus x2 theta 2 plus xn theta n. This is what we are expecting, and we are telling that this is the generalized representation for that. How is it possible? Is you can write x transpose as x1. It should be transpose, right? It should be written in this way, xn. This is transpose, and theta should be represented in the normal way theta, because it's not transpose. So this is going to be until theta m. So when you multiply this matrix multiplication, x1 into theta 1 plus x2 into theta 2, because we don't have any other columns or rows here, this is going to get multiplied in this way, and you're going to get the same representation. So in vector representation, you generally represent the product as x transpose theta. The same meaning, it actually gets the same meaning of this product itself, but for generalization purpose, we go for this representation. Is that x transpose theta representation clear? Wherever you go for deep learning courses, that representation is being used. Maybe you already might have known it, but I wished to clarify it. And you're adding the bias. So this is a summation part, and you're calling a G function here. That G function indicates the nonlinearity introduction. So the nonlinearity introduction can be used using many functionalities. You have sigmoid function, you have tan H function, ReLU, many kinds of activation functions are there. So the need of this activation function is what we discussed now. The different kinds of activation function that we'll see soon. So the sigmoid function as shown here, you can see that it is one. The actual equation for sigmoid is 1 by 1 plus e raised to minus z, where the z is nothing but this is what the summation stands for. Now, when you are approximating the relationship between x and y, you're restricting it to this function, but you're going to learn the parameters of this particular representation x. So you'll be learning what will be learned here. X is given to you. You're going to learn what the theta values are. Okay, with the help of the nonlinear function. As in linear regression, you had the equation of a straight line, and you are learning the coefficients and bias there. Similarly, here you are going to learn the coefficients and bias itself, but it is going to be plugged into this nonlinear equation, not just the linear equation. It will be transformed into this nonlinear aspect. So sigmoid function is one popular function which will introduce nonlinearity into your neural networks. And keep in mind that this nonlinearity combination, the summation and nonlinearity combination, is applied onto every neuron. It's not just restricted to the output layer, it's introduced into every neuron. At every hidden layer, you have to mention, when you write the code, you will have to indicate what activation function is being used there. Okay, so sigmoid is a particular function, a peculiar function that restricts the output value in the range of 0 to 1. You can see that the graph is an S-shaped graph. In logistic regression, you might have already seen what one second, I've got a very urgent call. Give me a minute. Sorry to interrupt, but is that fine, ma'am? Can I just?
Yeah, sure, ma'am. It's okay.
I'm really sorry. It was a very urgent call. That's why I interrupted. Really sorry for that.
It's completely fine, ma'am.
Okay, sorry.
It's okay.
Thank you. So we were. One second. I think the screen share ended, right? Share it one second.
Yeah, it's visible, ma'am.
Okay, thank you.
Okay.
So we were telling that for every neuron, this is applicable, that nonlinearity aspect and the summation aspect is applicable. Now we'll move ahead and see what all different kinds of activations we have. For sigmoid, you saw that it's a specific kind of nonlinear function introduced into the network with by restricting the range of values from 0 to 1. And other activation functions are actually linear itself is an activation function, but that doesn't do anything. It just transforms whatever summation value you got, that will be transformed to the output. So, but we do call linear also as a activation function. Then we have other nonlinear activation functions such as sigmoid, the one that we just now told, the limit is 0 to 1, and the equation also we saw. Then we have something called the tan H activation function. The equation corresponding to tan H activation function is e raised to z minus e raised to minus z by e raised to z plus e raised to minus z. Each of the z is a summation that we talked about. So when we are estimating the values, the model what it's going to learn is the theta values and bias value itself, but it is represented using this nonlinearity, so that the values of tan H is restricted in the range -1 to 1. In sigmoid, it is 0 to 1. Tan H is designed in such a way that it is restricted between -1 to 1. Certain activation functions are used in certain contexts, which we will learn later. Tan H is specifically used for RNN, recurrent neural network kind of functions. In the gated concept that is going to be learned as part of RNN, tan H comes in inbuilt in the recurrent neural network concepts. So each of these activation functions have to be used at certain contexts, and some activation functions can be experimented as part of the hidden layer concept as well. Okay, so two ways you can use, either based on the context, you will have to definitely use one kind of activation function in the output layer, but there are also situations where in the hidden layer you can experiment with different kinds of activation functions. Okay, so there comes ReLU, that is rectified linear unit. In ReLU, what happens is you're not restricting the, as in sigmoid, we are not restricting it from 0 to 1. The minimal range is restricted to 0, but whatever is the outcome of the summation, if that is a positive value, that is as such transmitted to the output. Otherwise, If it is lesser than 0, it is restricted to 0. So whichever is the maximum value, that will be taken into consideration as part of ReLU. But uh, in ReLU itself, there is another variation that is called leaky ReLU, wherein since when we started using ReLU, there was this issue of getting the results. When you take the gradient, the results tended, in certain scenarios, it tends to get 0. So for that, at least a small amount of value has to go through the neuron in order to ensure that we had something called leaky ReLU, wherein we pass in a small value, not just 0. It will just pass in some 0.01 value. That is called, or zero point 0.5. A small value will be passed in rather than 0. That is called leaky ReLU. Now, these are the common activation functions we just now discussed. So based on the problem type, you will have to fix on the activation function. As I told earlier, in certain contexts, you will have to use a certain set of activation function. And this applies to the output layer. This applies to the output layer. In the hidden layer, you can actually experiment with most of the activation functions. You can try sigmoid, you can try ReLU, you can try TANH in the hidden layer. That is fine. But when it comes to the output layer, based on the problem in hand, output layer also has a set of neurons that we saw earlier, right? Here also we do have certain neurons. So when it comes to the output layer, based on the problem that you have in hand, you have to ensure that the appropriate activation function is applied at the output layer. So for that, we do have this chart. You can refer this. If it is a classification problem, we do have different kinds of classification problem. We have binary classification, multi-class. As of now, you can ignore this multi-label classification. That is for one input itself, we can have multiple labels. You can ignore that as of now because we are just learning the basic concepts. So when it comes to classification, you can have two kinds, binary and multi-class. And when it comes to regression, again here sigmoid is also applicable. Sigmoid can also be used, but generally linear, if you have to restrict the values to 0 to 1. Otherwise, linear activation itself is used in the output layer. Linear activation is used in the sense, in regression, suppose it is wind speed prediction. You cannot say that you have to restrict the value to 0 to 1. So in that context, linear activation is used in the output layer. Linear in the sense, whatever comes as summation, that itself is transformed to the output. Okay, so if a huge value comes up, that will be transformed to the output. But in certain scenarios, if you have to restrict the output values in the range 0 to 1, in that case, in the output layer also, you may have to use sigmoid. Now, coming to classification, you can use sigmoid for binary classification because sigmoid functions in the range 0 to 1. So how do you convert this to binary? You can set a threshold. Above 0.5, you may say that it is a positive class, right? And above 0 or less than 0.5, you can say that it is a negative class. So you can transform a sigmoid activation function to a binary classification easily. That is why generally we use sigmoid activation for binary classification. But when it comes to multi-class classification, you have this concept of softmax activation. Has anyone heard of softmax activation? It's actually sigmoid itself, but the peculiarity is that when you have multi-class classification, what exactly is being output in a multi-class classification? Is it the actual label that is being output? What is being output? Yes, probability. Probability is being output, which means that if you have 5 classes and when you give a new input to the model, a trained model, you are going to get how many outputs? 5 outputs will be obtained. If you're taking a 5 class classification, did I tell 5? I think 5. So if you're taking a 5 class classification problem, when you give a new input into a trained model for that trained model for 5 class classification, you're going to get 5 outputs. What are those 5 outputs? For each class, what is the model predicting that the probability for assigning to that class be? Suppose one second. You have 5 class A, B, C, D, and E, and you have an input X. Sorry, input X, which is being given to the trained model. Okay. So what is being output is maybe 40, 80, sorry, now itself it's maybe you can make it 5, 35, 5 into 590. Okay, which means that all these are the probability with which this data point is going to be allotted to these particular classes, which means that the model is telling with 5% confidence that X belongs to A, model is telling with 80% confidence that X is belonging to B, model is telling with again 5% confidence that X is belonging to C, 5% confidence that X is belonging to E, another 5% confidence that X is belonging to E. This is what you're going to get the output as. Am I computationally correct? Okay. What is the peculiarity of this set of probability values? What peculiarity do you see here? What is the peculiarity of these 5 probability values? That screen went off. Oh, that, okay, fine. But 80, that blank screen actually went off. Fine. But just tell me what exactly was the peculiarity of those probability values. It was 80, 5, 5, 5, 5, right? When you sum it up, you're going to get the value as 100, right? So that should be ensured. That should be ensured. So what exactly happens in softmax function is you have the sigmoid output or the linear output. That particular output is transformed into a distribution function applying softmax so that you get a distributed set of values, set of probability values in such a way that the highest confident value will be having the highest probability, and the sum of the probability values that you have got in the final layer will be 1 or 100, whichever it is mapped to. So that is ensured with the help of softmax activation. Softmax activation is nothing but the previous layer handles the actual classification with the normal activation functions that we discussed till now. But final layer softmax, what it does is it ensures that this particular output is transformed into 5 confidence scores or probability values in such a way that when you sum it up, you're going to get the value as 1 or 100. That is taken care of by the softmax activation. Is that fine? Why 5 is that? The example that we took now is of 5 classes. So is that clear why we are using softmax activation for multi-class classification? We should have that transformation there. Otherwise, any simply any 5 set of values, if that comes up, that doesn't map for any confidence. It's just random values. When you sum it up, it won't even give you probability as 1 or 100. So that should be taken care of, which is ensured by the softmax activation function.
Ma'am, could you please explain that softmax activation once again?
Yeah, sure, sure. I'll just include the equation as well, which I didn't actually do. Can you give me a minute? I'll just take it from the internet and I'll share. One second. I'll just share the screen soon. One second. So when it comes to multi-class classification, as we told just now, suppose we have 5 classes as we just now described. We have the input value. You have a model to which this input is given, the trained model, multi-class classification model. And I'm telling you that we have 5 classes. So we have A, B, C, D, and E. 5 classes are there. And suppose you're getting the outputs as 5%, 80%, 5%, 5%, and 5%. So this is how your output for multi-class classification looks like. You cannot expect that your model is going to give you directly that, okay, this is the input, it is going to be mapped to B. It's not like that. You're going to get probability values or the model confidence scores in such a way that the model is going to assign, or model is confident, 5% confident that this input value is going to be A, or the model is 80% confident that the input value is going to be B, and so on. Okay, so the peculiarity of this output is that when you sum this up, it has to be 100, or if it is a normalized score that means 0.05, 0.8, 0.05, and so on, then it's going to be, the sum is going to be 1 or 100. That should be ensured. Who will ensure this? You should have a function that is corresponding to taking care of ensuring that this output is actually what happens is in the previous layer you're going to get a sigmoid output. This sigmoid output is actually transformed to the softmax function. Okay, the learning process actually happens in the previous layer itself. But why do you have to have a softmax function at the end layer or the output layer is that this probability or the value that is coming from the previous layer has to be equally distributed. Not equally distributed, has to be distributed in such a way that uh, the class where the model is more confident has to get the highest score, and the remaining confidence has to be distributed in such a way that when you add it up, you're going to get the probability as 100%. So this distribution from the previous layer to multiple classes, this is taken care of by the softmax function. This is the softmax function. Here you can see that every individual value is divided by the sum of the values here, so whatever input that this output layer receives, that is taken and it is divided by the sum of the entire number of outputs, which will ensure that once you get all the probability value, when you sum it up, you're going to get the value as 1, or if you're converting it into percentage, it's going to be 100. Okay, so here if you take 5 by 5 plus 80 plus 5 plus 5, that is going to be ensured that every class gets a ratio of the entire output that is coming in the previous layer. You get a small idea?
It's clear now, ma'am.
Okay.
Thank you.
Okay. So that is the case with softmax function. So why do we use softmax for multi-class classification is that you have multiple classes and you have to ensure that the sum is 1. That is the only case why. Otherwise, the remaining learning principles are same as we do with the binary classification or even regression. The learning principles are same. Just to make it into classification, multi-class classification, we are adding the softmax activation there. Okay. So as we spoke about activation function, we do have something called loss functions as well, which we have to see soon. Before that, okay, one more concept that you have to learn is these layers are also called dense layers. That is what is indicated here. Why is it called dense layer? Is that we are connecting all the inputs to the hidden layers. All the hidden layers are connected to the output layers. So this layer is actually called it's called hidden layer, but it's also called these kinds of layers. All the hidden layers which are connected to all the input and output, these are called dense layers as well. Why? Because every connections are established. If it was sparse, the opposite of dense is actually sparse. Sparse indicates there are situations where we have to use sparse connections when you have to regularize the training process, which need not be looked into now, but keep in mind. Sparse connections is when all the edges are not connected. Some of the edges are left out just to understand or make the model understand the importance of those connections. That is a different principle which we are not talking about now. But why is it called dense layers is that every edges nodes are connected to every other nodes in the hidden and output layers. Okay. So this was something that we discussed earlier. We have a forward pass and the backward pass. So in forward pass, we have all the multiplication, addition, and the nonlinearity application. Then we transform the input into the output. And in the hidden or in the backward pass, we compute the loss and then we back propagate to update the weights. So we have to understand how. So this was the previous example that we have already discussed. I'm not explaining it again. So we have to learn to understand how to compute loss. That is also a very important concept when it comes to deep learning. So if this was a very simple neural network. Suppose when you are giving an input, here you can see there is a data that is represented here. X value is 1800, x2 is 600, and y value is 330. This particular example is what we are trying to take here. And if this is here, you can see that x1 and x2 are just two features. So your input layer requires only two features. That is why we are taking only x1 and x2, two features. And this is a regression problem. So you just have one y value, right? One y value. and you ensure that the activation function for this y value is going to be linear, so that it is not restricted to any set of values like 0 to 1 or -1 to 1, because here the set of values is not restricted, it can be any value. So you are trying to make the model learn such a data set in which it is a regression problem. So you are just connecting the input two values to three neurons in the hidden layer. Now most of the people have doubt in deciding what number of neurons has to be kept in hidden layer, how many number of hidden layers are required for a neural network. All these are kind of experimentary. If you have a huge data set and you have complex patterns to learn, you do have to make sure that you have more layers. But if you have a very not, I mean, generally we don't go for deep learning models for very small data set, but at least suppose only hundreds of records are there, you need not go for a lot of layers. Maybe the model itself can learn from a single hidden layer with some 10 neurons. That will be enough. But we have to experiment it and try out. Maybe the pattern hidden in those hundreds of records might be complex. If that is the case, you may have to have more hidden layers, or maybe you have to increase the number of neurons in the hidden layer. So you have to start with something, try out different combinations, and you have to analyze whether the results are improving or it is getting decreased. In that way, you have to decide whether you have to move ahead with increasing the number of neurons or reduce the number of neurons. These are random and experimental. You have to keep experimenting, and then only you can find out the how to decide onto a deep learning architecture. Okay. So here what is happening is we are providing an input value 1800, 600, and the model, you have certain set of initial values with which the model has predicted the value as 300, but we know that the actual value is 330. 330 is provided to you, so the actual value is 330. So what is the loss here, or what is the error that you found here? You have the input 1800 and 600. You are taking that particular input, you are passing it on to the neural network. You have certain initial values, so initial weight values there. Your model in the initial forward pass, it predicted the output value as 300, but the actual ground truth value is 330. What is the error there? 30 loss. Yeah, 30 is the error there. It's not the actual loss, but I'm telling you for that particular data point, the error is 30. So but during the training of a deep neural network, it's not just one single data point that you're focusing on for computing the loss. You have to focus on the entire data set, or at least a data set that you have taken entirely for training. Imagine this set of data was taken for training. So what happens is every data point has to be fed into this neural network. Every y values have to be noted down. Every predictions have to be taken. You have to find out what is the difference between the predicted value and the actual value. You're never going to get the exact value actually. Okay, this is just for the visualization purpose. Somewhere and all, you can see that the exact value has been got, and for some others you can see that there is a distance there, there is a difference there. So here value difference is 10. Here you can see there is a difference of 20. Here you can see a difference of 10, 20. Here there's a huge difference, right? You can see a difference of 300, I think. Here you can see a difference of 10, and so on. So these are the difference values you get for the entire data set. You have to apply a formula which is the standard formula for as that will function as the loss function for the training of the neural network. So when it is a regression problem, the loss that we focus on is called the mean squared error. You're not just simply averaging this loss. Instead, you are going to consider the mean squared error, which means that you are finding out the loss values, you are squaring it up, and then averaging. Why we are squaring is, one is for quantifying the difference in values so that you get a clearer picture of what is the exact loss, because it may not be this huge. When it comes to reality, it may be just simply 0.001 or just 1 or 2. So you have to get it quantified to decide whether you have to go ahead with the backpropagation or training. Another reason is due to the negative value. So you generally go for squaring. It's like taking the absolute value, you just square it and then take the mean value. So mean squared error is the normal standard loss that is followed for regression problems. So when we are training a neural network, our ultimate goal is to reduce this mean squared error and to find the global minimum using the gradient descent. This is the case with regression problem. So for regression, did you understand why we are going for mean squared error? So once this error value is found out, in one iteration, you have something called back propagation, with which you will update the weight values in the previous layers. We'll come back and then again compute the forward pass. Again, we'll be finding out predicted values, actual values. Again, we'll be computing the loss. You'll be comparing with the previous iteration in graphically. You'll decide whether you have to go ahead, because you might have seen that the loss from the previous iteration has reduced, so you can go ahead again, which means that there are chances that if you further train, your loss is going to again get reduced, so you keep on moving ahead, right? So that is how the mean squared error is used in regression. During the backpropagation, what happens is the gradient descent algorithm is applied, the weights are updated, and the gradients are used for updating the weights, again forward pass, and this thing goes on. Now, when it comes to classification problem, you can see an example there. It's a binary classification problem. So again, you're just using only one output neuron here. You have certain set of inputs, and your y values are in such a way that those are labels, 0 or 1, positive or negative. But what is the output that you're going to get? What is the output that you're going to get? The output that you're going to get is again probability, as in multi-class classification people have told. You're going to get the output probability values, which is normalized here. So if your output is above threshold is above 0.5, you say that your class label is 1. If it is less than 0.5, you're going to say that your class label is 0. Okay, so the probability values predicted for this particular data set is this, and the actual values are given here in blue. So when you compare it, you can see that when the probability is 0.2, your class predicted is 0, and your actual output is 1. So what should be the loss here? You cannot simply subtract it and say that 0.8 is my loss. It's not 0.8 actually, right? You get the class label, you have the probability value. You shouldn't be directly finding out the difference here, or as we did with regression, you cannot simply subtract here, because we are dealing with probability and class labels. So in that case, there is another loss function that you have to focus on, which is called the binary cross entropy. This is also called the log loss. Logarithm of, we dealt this in decision tree also. In decision tree, we had taken predicted value into log of that particular value. The same concept is actually being applied here, but not entirely the same. There, the requirement was different. Here, we are trying to reduce this binary cross entropy loss with the training of the model. Okay, so for regression problem, we are focusing on mean squared error. Actually, other types of errors are also there. Mean absolute error is there. Root mean squared error is there. Generally, we go for mean squared error. Other error values are also there. You might have learned in evaluation metrics yesterday when Jisha ma'am taught. When it comes to classification, binary classification, the error that we are, or the loss function which we are trying to reduces binary cross entropy. One second. Is my screen shared? Yeah. Okay. So that is
Yes, ma'am. Yes, it's visible, ma'am.
yeah, thank you. So that is binary cross entropy. Now, what we are trying to do is we are trying to find out the minimum value for whichever loss we are focusing on, whether it is binary cross entropy or mean squared error. We are trying to reduce that loss. So whenever we are speaking of loss, you should be familiar with this usage, J of W. J of W will be the indication of loss. J is the loss function, W is the parameter that we are learning. So for a particular set of weight values, for a particular iteration, what is the loss that was incurred? That is represented using J of W. So our intention is to find out the set of W values for which this particular loss will be minimum. The set of weight values for which the loss value is going to be minimum. Okay, so after the iteration or after the learning process, what we are left out is with the set of weight values. So every time for a given set of weight values, when you compute the loss, you are trying to find out the minimum weight value with which, the updated weight values with which the loss function is going to be the most minimum. Okay, that is the learning function. Then gradient descent in a very simple way, I'm just mentioning. you have the initial weights randomly. Probably ma'am might have taught it yesterday, but this is just for your for deep learning. Teaching gradient descent will go out of scope because that itself takes a single hour of session. So I'm not going into detail, but compared to machine learning, what minimal you can learn, that I'm sharing it now. So you initialize the weights randomly from a normal distribution to all the weight values that is there in the neural network. Now we have to repeat this until convergence. What are you going to repeat? You're going to compute the gradient. Why do we compute the gradient? Is that this gradient is used for updating the weight values. Okay, gradient is nothing but you're finding out the differentiation of loss value with respect to the weight values. What is loss? Loss is represented with the help of weight values itself, or loss function depends on the weight values. We are computing the loss based on the weight values. Why? Because loss is nothing but something that is computed as part of the forward pass. In the forward pass, x1 x values or the input values are already known. The only thing that is varying is the weight values. So loss depends on the weight values. Whenever weight changes, loss changes. Nothing else is changing. Input is not changing, right? So whenever weight value changes, your loss is changing, which means that j or the loss function is purely dependent on the weight values. Once the deep learning model is trained, w is the one that is being updated, and w values are the ones that we are trying to reuse. Okay, so we are using this gradient, that is the difference of loss function with respect to weight values. We are using that directly for updating the weights. So compute the gradient, and you're trying to update the weights using the gradient value that we have obtained. A very minute value we are using, and you're going to update the weights at each iteration. You can see an eta value here. This is called the learning rate. There is something called learning rate, which is used for updating the weight values. Why do we use learning rate? Is again that comes as part of gradient descent. You might have seen a curve yesterday. Did ma'am teach it with a curve, the gradient descent part?
No, ma'am. No, 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 ma'am.
Okay, okay. So actually, suppose you have a set. This is the imagine this is the gradient. This is actually the 3D view of this gradient descent itself. Okay, you're fine. You can see a small parabola here, right? So this is the weight values, and loss is being plotted as the y value. What happens is, for every weight value, every weight indicator, you are updating the weight, loss is getting reduced. Again, weight is updated, loss is getting reduced, and this moves down until the loss reaches this minimum. This is what our expectation is, but in reality this is not the curve that you're going to see. You're going to see a curve which has lot of minimas, local minimas. You have to find the global minima, but that's a different challenge which we are not talking of now. But this is the concept. You have a curve, you're going to reach the local minima. So there is a deep slope here. You have a deep slope here. You also have a shallow slope at this point. At this range, at this area, you have a shallow slope. Here, it's a deep slope. So when you're nearing the global minima, your slope is going to get lesser. You're going to get a lesser slope, but at the initial points, the slope is higher, right? You have a steep slope here. So you don't actually have to take equal steps every time you update the weights. You don't have to go take equal steps. You know that you have to reach the lesser slope. So only then you are going to reach the minima. So you can jump through here. For jumping there, you have something called the learning rate. Instead of going through every single iteration, you can have a learning rate which will help you identify that this is a steep slope. There you can take higher steps, but when you come to the what do you call it, shallow slope, there you can take smaller steps so that you don't miss this minima. If you take steeper steps here, what happens is you might jump through the minima and you might reach the other part, so you will miss this minima. So here you have to ensure that you take tiny steps, but at the initial portion you can take bigger steps so that time can be saved or the number of iterations can be saved. So that is why we have something called eta, or this is called the learning rate. Okay, with the help of learning rate, you ensure that when the slope is higher, you take big steps. When the slope is lesser, you take baby steps. Just at least the takeaway is that learning rate is used for optimizing the learning curve. At least that much, if you can take, that will be fine. Even if non-linear is not there, this function will work. But the thing is, it will take more time to converge. Model convergence is achieved when the loss is at the global minimum. Okay. Then, so in the initial, in the forward pass or in one iteration, what happens is gradients are computed, weights are updated accordingly with the help of backward pass, and the weights are returned. This will continue until convergence. Convergence means you ensure that the loss function that you have got is minimum. Okay. So just a basic idea of what back propagation is, I'll just show you. But then we are not going into the pure mathematical aspects. There is something called chain rule, which has to be what do you call it? You have to understand what chain rule is, at least at the surface level. So in forward pass, what happens is you have the x1 value, w1, z1, w2, y hat, and the loss function. These many concepts are there. W1 is the weight that associates x1 to z1. Z1 is the neuron in the hidden layer. Z1 to output layer, you have something called w2, which is the weight that is associated with on the edge that connects from the hidden layer to the output layer. This is just one linear connection. You have tons of connections of this form in a proper neural network. We are just taking one and we are going to learn. So once this forward propagation is achieved, you have something called the loss that we have computed, that we are computing. Okay, so we always keep on telling about some gradient, right? We are telling that loss depends on weight. So you are going to compute the gradient of the loss with respect to weight, which will help you give the value with which you are going to update the weight. But it's not directly possible to find out the gradient of weight with respect to a gradient of loss with respect to W2. You have to apply the chain rule there. Okay, so at least keep this figure in mind when you have to find out the gradient of the loss function j of w. You have to do it in a chain format. Dou j of w by dou w2 is not directly possible. Instead, you have to go for dou j of w by dou y hat, dou y hat by dou w2, partial differentiation of y hat by w2. Why we are talking about this is that if you want to find out the gradient of j of w with respect to w1, again you can rethink of this chain rule. What can you do? You have to apply dou j of w with y hat to w2, w2 to z1, z1 to w1. That is how that uh, chain rule actually functions. This chain rule, basic, I have just taken the surface level of this chain rule. I have not talked about any derivation, but at least understand how this chain rule functions. Okay, at least you should know that you are going to update w1 and w2. So with what you're going to update it, you're going to update it with a gradient. Gradient is computed as the differentiation of the loss function. So when you talk about updating w1, you have to update it using dou j of w by w1. This should be there. So when you need to compute this, direct computation is not possible. You should have the chain rule applied. Dou j of w by y hat by w2, w2 by z1, z1 by w1. So you will get a longer term which we use to update w1. So for the entire neural network, just imagine how many such computations will come up. So it's actually represented using a great matrix, and a lot of multiplication and additions are incorporated. Uh, so at least for dou j of w by w2, that gradient part is clear. What I'm asking is the previous step, this one. If you want to compute the gradient of loss function with respect to w2, the chain rule applied is dou j of w by y hat by w2. This is what is computed, and this gradient is used to update w2. So the same process is repeated when you have to find out for w1. You have more chains attached, and you are computing the gradient for w1 in order to update the weight w1. When you do some problems related to this, obviously this is going to be more clear, but at least now get an idea on why this chain rule is used. What are we aiming at? We are trying to reduce the loss. Gradients are used for updating the weights. Once the weights are updated, what you're going to do? You're going to again forward pass apply multiplication and additions and find out the forward pass value, again compute the loss value, again compute gradient, again update weights, and so on. This will go on for every iteration. Okay, getting the concepts at least on a surface level. Don't think about the actual computation of it, but sure. But unless you try it out with the mathematical values, you won't be that expert. When you listen to it, you may feel that you're getting, but you have to try it out. Okay, you will get it, but I was just ensuring that you have understood what the chain rule is. Fine. So until now, what we have discussed is what the progress of deep learning and where we are standing, what ML and DL difference is, and we spoke of some activation functions, what is loss, a quick recap of gradient descent and how we apply it into deep learning models, what backpropagation is, and the chain rule. This much is what we have discussed till now. So before moving into the different types, so the neural network that we discussed until now was the feed forward neural network. It's called the feed forward normal neural network. This one. We have just neurons, edges, and the hidden output and input layers. But for different modalities of data, the one that we saw just now is for the normal tabular data structure, CSV files or Excel files that we have spoke of. But when it comes to different modality of data, suppose if it is an image data that we are taking into consideration, we have popular specialized networks for image data as well as video data or time series data. We have specialized neural networks for that. We have before moving on to those the basic concepts of those neural network architectures, we have to see what these modalities are or what the peculiarities of these modality of data are. So tabular data is what we just now saw. I'm not going to describe it again. So there are pre-processing techniques that you need to apply onto tabular data. Maybe that was covered as part of pre-processing techniques. That was important. Pre-processing is taught to you. Pre-processing is actually a very important topic. I just wanted to know whether it is covered. No, data pre-processing is not covered. Okay, okay. So I think that was not part of the syllabus. Actually, pre-processing was also, and maybe that is not possible to cover within the stipulated time. But just keep in mind that there are certain algorithms or strategies that you have to apply before applying any deep learning or ML model. You have the cleaning, data transformation part, label encoding, how to smooth out nice, what all kind of pre-processing you have to apply. Based on the modality, these pre-processing techniques will also vary. So this itself actually, I'm not detailing, this itself actually takes maybe half an hour to show what all kinds of abnormalities will be there in a data. So this is for tabular data. When it comes to image and video data, you should have specialized architectures as I told earlier. So image and video actually comes under, we can also call it visual data, and it actually comes under a branch of study called computer vision. Okay, computer vision. Although computer vision is not completely under the deep learning control, we do have conventional methods also there. Image filters, and handcrafted feature extraction, handcrafted filtering. All these are still there. If you go for using OpenCV framework, you do have conventional methods for computer vision processing, which doesn't use any deep learning techniques. Handcrafted filters, handcrafted techniques are still there for segmentation purpose and all. But still, before moving on to the specialized architectures, you should know what computer vision discipline leads or where it is heading to. So computer vision, any idea? Anyone working on computer vision or visual data? No, you have not. No one has heard of image and video data, I suppose, right? Okay, anyway, computer vision is a branch of discipline, or it's a discipline that deals with how we make the systems understand the visual world, or the computers understand the visual world, which means that if I or we can see a cat and identify, and our brain is identifying that it is a cat, how the system is going to process it when you are feeding an image of a cat to the system or the computer. it will be read as a set of numerical, it is stored in the system in the form of a set of numerical values, right? It is stored in the system in the form of a set of numerical values. Hope that is known to you. An image, when you read into a system, again, if it is not known to you, I'll show you with an example that is also there in this slide. So when you're reading an image and storing it in the system or the computer, it is a set of numerical values. From that numerical values, you're trying to formulate or design algorithms in such a way that the system is able to identify that it is a cat present in that image. Okay, so that is how computer vision works. We are trying to deal with algorithms that would help the computers understand the visual world. So that's just an example. Today, where computer vision has reached is far from imagination, as I told from the initial session itself. It it is in such a way that the system itself can, the algorithms right now can automatically identify different events itself in a video. It's not just a cat or dog that we're talking about. We are discussing of different activities that are present in a video, and that itself is done in real time. Okay, so to gain high level understanding from digital images and videos is what we are aiming at as part of computer vision. So, just a quick idea into what is the difference. In our case, if you are viewing a cat, brain is actually sensing that, eye is actually sensing that it is a cat, brain is interpreting that it is a kitten, and the we are understanding that it is a cat there. But when you are reading a image file of a cat into the system, this is how it actually looks like in the system. Numerical values, 1.5 points, and you can see those values there. And if it is a grayscale image, you will have just one channel. If it is a color image, you are going to have three channels: red, green, and blue. And a combination of these values will give you the actual set of values. Those numbers are nothing but the brightness or intensity values. So how intense is the red component in a particular pixel is there? That is what is indicated those in those numerical values. So understanding how the image data is represented in the system is crucial before understanding how convolutional neural networks function. I cannot directly say that this is CNN and this is how CNN works. That's not possible. That's why I'm just taking it to this level. These numerical value representation is how it will be stored in the system. So when it is color image, you keep in mind that you have RGB components. You have three channels, and when it comes to grayscale, it's just one channel. Another important difference between the tabular structure that we spoke of earlier and the image structure that we are speaking of now is that in tabular structure, one data point is represented as a single row, right? A single row. But in image, you can see that even if it is grayscale, you definitely have one data point itself is two dimension. You have number of rows and number of columns that will be there. So you cannot have a simple deep neural. I mean, it's not like you cannot have. You can have it, but you have to transform this image into a flattened structure. Then only you can use normal deep neural network for processing images. Okay, right now it has a dimension of two. The number of rows and number of columns is there. You cannot feed this data directly into the neural network that we saw earlier. This one. Here you cannot directly feed it because x1, we don't know what value x1 can take because it's a form of a square structure, right? What value you're going to feed to x1, what value you're going to feed to x2. So unless you flatten this image representation and maybe make it, suppose it is the size of 5 by 5 image. Suppose it is 5 by 5 image and you're trying to flatten it and make it some 25 by 1. 5 by 5 means it has 25 values and you're making it flattened, then you can go for the feed forward neural network. That is fine. Unless you are not flattening it, you have to use specialized architecture for processing data from this images. So why don't we go for flattening? That is another question. We'll see that soon. Okay, so I hope you have understood the color channel representation. So in a system sensing devices camera, then interpreting device is a CPU that need not be mentioned. Now, suppose this is an image of Taj Mahal is shown there. You can the grayscale representation is also shown there. Numerical representation is also being shown there. It's just for visualization purpose. Don't stick on to the practicality of the values given there. Don't think about it. It's just for visualization purpose. As I told earlier, you could have thought about flattening those values and go for normal deep neural networks, but we don't do that. Why? Because from images, when you try to extract features, the spatial information or the neighborhood information is important. What that means is that In tabular data structure, we were focusing on just the rows, right? And it had input features, each column wise features were there. Here we are not talking about the column or row. Here we need spatial representation. So suppose we are creating an image classification model where you have to classify this as monument. So there should be some features in this image that would help you classify that this image is a monument. How do you do that? So imagine one important feature that this would be classified into a monument is that this presence of this particular dome. You can see that there is a dome here. That might be one reason why this image is called a monument. So if you have to identify this dome, it's not just with the help of any row or any column. It's a combination of rows and columns that is being used to identify that there is a dome like structure here in this area. In this area there is a dome, in this area there is some peculiar representation. So there neighborhood pixels play an important role to identify that it is a dome or it's a particular structure there. Here also one particular structure, peculiar structure is there. That is identified with the help of the square regions. It's not just a column. If you simply take a column or if you simply take a row, you may not be able to identify such a feature from that image. So in that case, you cannot just simply flatten and feed it into a deep neural network. You may be able to do it, but you won't come up with good results. So for that, scientists have chosen to, they come up with new architecture called convolutional neural networks, wherein there is something called a filter. There is something called a filter, which this filter is responsible for extracting features from localized region. You have a filter maybe of size 3 by 3. This image is maybe let it be of size 100 by 100. You have a filter of size 3 by 3, which is convolved over this image, and important features. So some operation is done. I'll tell you what that operation is in the upcoming slide. Some operation is done, and features are extracted from localized regions. That is the peculiarity of convolutional neural network. Why is it called convolutional neural network? Is that this operation that I just now mentioned, the filter application and the operation that is performed is called the convolution operation. There are controversies regarding the naming of that operation that I'm not going into deeper now, but I just mentioned it. If at all some of you at least know that it is correlation, I just wanted to mention it. But this is what is happening. You have filters of different size of just maybe number of filters will be there. Each filter might be responsible for extracting meaningful features from the images. Okay, so before moving on to the actual convolution operation, I'll just tell you one more thing. Videos are also part of visual world. So when I spoke of images, we talked about two dimensions. But when it comes to video, we have an additional dimension that is called the temporal dimension. What is a video? Video is a collection of images which is sequentially arranged. Right? It's not just simply some random collection of images. Video is a set of images that are sequentially arranged, which would give you some continuity or motion factor. So there is an additional dimension there, that is a temporal dimension or the time domain. Okay, that is how videos are dealt with. So you have spatial domain that comes in the image as well as a temporal domain is also there. Just understand that this is the structure of videos. We won't be going into deeper aspects of videos. Right now, what we are going to do is we are going to learn about convolutional neural network that is meant for images. Okay. So I told that up until now, the only thing that I've told is when it comes to images, spatial information is important. At least that much have you got? Like spatial information is important when it comes to feature extraction and image. What we are talking of now is the specialized neural networks called CNN and RNN. With CNN and RNN, I might wind up. I just want to give you a surface idea of how images are represented, how videos are represented. Then I'm just talking of how convolutional neural networks are represented. And I was telling that from images, when you're trying to extract features, spatial information or the neighborhood information is important. Is that somewhat clear till that? Why spatial information is important or why that neighborhood information was important? I was telling that the Taj Mahal image that we showed, if in order to identify that it is a monument, there should be some regions that would help us identify that there is a specialized corner there that would help us map it into a monument. So for that, we should have some feature which would help us identify that there is a, representation there. For that, we do use filters, handcraft. We do use filters or kernels that we convolve over the image, and we identify that there are features from the images. Okay, so at least the importance of neighborhood information is understood. When you see some more example images that I am about to show, I hope you might get a better picture. No one is answering. I think everyone is fed up. Ma'am's class has gone out of. I can understand that it's a huge transition from ML to deep learning. Okay. At least a surface level idea if you get, that will be well and fine. So a normal convolutional neural network structure is of this form. You have a convolution layer, you have a polling layer and multiple combinations of those. Then we have the fully connected layer and the output class layer. We'll come back to this architecture and explain this to you once again. But before that, you should identify or you should understand why we require kernels. Why we require kernels. So kernels are filters. I was talking about filter. So what we are actually doing is, before moving this is the image that we are talking about, Taj Mahal. And when you apply a filter, this is a filter of size 3 by 3. And as I said earlier, when this filter is applied onto this image and convolved, when you convolve, you happen to do a process called Hadamard product. This is called a Hadamard product, which means that what you're exactly doing is your kernel is having some set of values. Here we saw that the set of values is 1, 1, 1, 1, 1. Okay. This particular kernel is passed on to this input image. So when you are passing it, you can see that the computation performed is A into W plus B into X plus E into Y plus FZ, which means point by point multiplication and addition. Okay. So when you apply this filter onto this entire image, you get 6 set of values. Why? Because you're striding it just one. This is the first location. This is the second location. This is the third location where you apply filter. I'll just erase and show it once again. This is the first location where you apply filter. This is the second location where you apply the filter, because the size of the kernel is 2 by 2. So you can apply the kernel only onto 2 by 2 locations. That is how you get 6 values. Okay. So the product, the operation that is performed is the Hadamard product. That is the summation and addition. Sorry, multiplication and addition. So when you apply, so there are certain conventional filters that you can use for certain purposes. So if you want to blur an image, you have a filter which will give equal weightage to all the pixels. That is what is represented by this filter. Right. If you want to blur an image, you shouldn't have any artifact that stands out. You want to equalize all the values. So for that, you are applying this filter where all the weights are equal. These values are also called weights. When you apply multiplication and addition onto this particular image using this filter, it actually blurs all the image because the weights given to all the neighborhood is equal. That is why it is getting blurred. Similarly, if you want to sharpen the image, it means that you are going to reduce the impact of the neighborhood part and you are increasing the impact of the center pixel of interest. Okay, that is how we are sharpening the image. You can see that the image is sharpened here. It's just an example for visualization purpose. I'll close this. I hope the screen is shared, right? Yeah. So in this case, you can see that this particular filter is designed in such a way that the middle portion is having highest weightage and the remaining part you can see that it is having deliberately lesser weight. So this filter is handcrafted in such a way that when applied onto any image, it will sharpen the image. Is that fine? So these are handcrafted filters which will help you perform certain feature extraction. So here another filter wherein the center portion is reduced to a huge extent and the remaining portions are equally weighted. Such a filter when applied onto this image, it will fetch out or it will filter out the edges from the image. So edges are filtered out or edge feature is extracted. So filters when applied onto image performs different functions. That is a takeaway here. Now The importance of these filters or kernels when it applies to deep learning is that the filters that we saw just now had handcrafted values. What if this handcrafted values are not possible and these handcrafted values are learned by a model, right? Because we cannot insist that always a model has to learn edges, or the model has to learn texture, or the model has to learn the color. You cannot insist what feature has to be extracted. That is the beauty of deep learning models. We are not telling the model to learn something. Model itself is learning whatever is relevant for mapping the input and output. So instead of insisting or using handcrafted filters, what we're trying to do is we're trying to learn the filter weights as we did with the, normal neural networks. These weights are initialized randomly, and you're using multiple filters, applying that onto the images and mapping it onto the output, back propagation, and the remaining things, training and all, everything remains the same. The operation is convolution, but the only thing is the the kernels that you're using is in such a way that the weights are learned in the process. It's not hand coded. Okay. So that is what is happening here. You have an image, you have a set of filters, it's not just one filter. Each filter is responsible maybe for extracting different features. So you have a set of convolutional filters, you have a set of pooling operation. Pooling is again another thing, wherein there are different kinds of pooling: max pooling, average pooling, and everything is there. I'll just show you it with an example. So if this is the convolved result after convolution, what max pooling does is, suppose 2 by 2 is the size of max polling. You consider 2 by 2 region from your image, whichever is having the um, maximum value, that will be considered in the result. Okay. Then what happens? The size of the image will be drastically reduced. Because every 4 by 4 regions you will be taking only the maximum value. So that's what happens is the size of the image will be reduced to the maximum, to a particular ratio. So pooling operation will be there. So a combination of convolution and pooling will be repeated any number of times. Any number of times it can be repeated. The number of convolution can be repeated any number of times. That is how a CNN architecture is formulated. So that is the CNN part, but you cannot complete this architecture without a fully connected layer. That is the importance of a dense layer. How does this neural network look like? This neural network is kind of the same that we learned for tabular data structure. So you should have a fully connected layer also for completing the training process. So why is it required is that, as we told, after the pooling layer, again you are having some square or it's not just one dimension, you have multiple two-dimensional values, right? So those values cannot be directly fed into this fully connected layer, or that cannot be directly attached to output class. You should have a fully connected layer in between, maybe just with one hidden layer, but you have to transform those square or two-dimensional values into a dense vector by flattening it. uh, you might feel it a bit complex, but you might reach a stage where your pooling values might be of 2 by 2 dimensions. So what you're going to do is, these four values will be made to straight 4 by 1 vector. 2 by 2 is converted to 4 by 1, every 2 by 2 is converted to 4 by 1, and it is combined to a single vector value, and that is attached to the fully connected network. It is again attached to the output class, and the training is incorporated. Okay. So how was it different from the previous neural network is that you have a set of convolution and pooling operations that is directly applied to the image data set, after which it is connected to a fully connected layer, but the training is getting performed together. Like when you train the model, one forward passes when the convolution layers are computed, and then it moves on to the fully connected layer, output is computed, and then back propagation is applied to the overall network. It's not two pieces. When you write the code, it's just a single architecture. Concepts are different. That's all. Got a surface level idea. I think that it might be, I mean, you people might be overloaded, but just listen and try to get a surface level idea of what a convolutional neural network is. Got it? Not the maths part behind it, but at least how features are extracted from images. Okay. So shall I move ahead with the recurrent neural network part also?
Yes, ma'am. Sure.
So when it comes to images, when we talk about features that are extracted from images, there are it's not like we do have a lot of different features that we talk about in images. When you are trying to distinguish between orange and apple, there might be some texture difference between these two. There might be color difference between these two, or edges might be of important feature when it comes to image classification. So the set of features that you are focusing on when you are trying to learn features from images might be limited. It's not like the tabular data structure. In tabular data structure, the different columns in every data set is different, right? But when it comes to images, the features that we focus on might be edges, blobs, texture, color, uh, or contours, or the shapes that is present in the images. There is a set of possible features that we might be interested in. So due to this concept, or due to this apprehension, you have the concept of uh, reusing trained models in images. When you have a model, a convolutional neural network model that is already trained on thousands of class, you can believe that that model is capable of extracting all kinds of features when it is being applied to different domain. You can reuse that trained model and apply it by fine tuning it into our data set. That is why we have this concept of pre-trained learning, where we transfer the learning that has already been done on another set of huge data sets. The reason is that the features that we are interested in when we are learning features from images, that is limited or that is reusable. Okay, just keep that in mind. I think transfer learning is in detail being taken by Suchitra Miss. I saw that in the schedule, so I just wanted to tell this. And it's not that every time you should have you have a convolution, a max pool should be accompanied. There are certain architectures that have successfully found results with multiple convolutions together, and then one max pool applied after convolution. So the architecture can be anything. You can experiment in different ways and find that how find or analyze how results are varying. That is the case with convolutional neural network. Now coming to recurrent neural network, we are talking about recurrent neural network next. Until now, we spoke about tabular data structure, then we saw image data structure and visual world, wherein we were talking about image and video. Now, in certain data structure, the sequence actually matters. Suppose there is an example that is given there. The movie was boring and long. You want to classify this comment as a positive or negative comment. Okay, so movie was boring and long. Actually, it is a negative comment, right? So how do you create a classification model with this input? These are not just one row, it's a sentence, right? It's not just one value that you are interested in. You have to have a combination of values that would predict that the sentence is of a negative impact. So there is no fixed size for this, there is no fixed set of attributes for this. On the go, when input comes up, your model has to classify that the sequence indicates that the emotion in this sentence is negative. So there are certain scenarios where sequence has its own importance. When sequence learning or features from sequences has to be extracted, you go for something called recurrent neural network, recurrent neural networks. The peculiarity of recurrent neural networks is that there is a recurrent connection format that is present in the recurrent neural network, which will take care of extracting features from the long sequences that is fed into it. Okay, so these sequences need not be just text; it can also be from videos. Video, as I told earlier, it's a sequence of information, sequence of images. So features to be extracted from images has to be taken care of by CNN, as we told earlier, from convolutional network. But additionally, you should have a recurrent neural network that would extract features from the sequence. Why do we need it? When you have a action that is performed in a video, maybe the Surya Namaskar that is shown there, how do you classify that this action is Surya Namaskar? You should have a set of frames there. You should have a sequence of frames there. Only when that is complete, you can say that it is Surya Namaskar or another yoga pose or any action. If you are trying to classify a hit by a person, one person is hitting another person. If that needs to be identified as a hitting action, you should ensure that a sequence of images is passed on to this recurrent neural network. Okay. So that is the importance of recurrent neural network, wherein you have, this is what is the actual representation of a recurrent neural network. You have a sequence of representation here. You have the input, one input is fed into the hidden gate there, and the features extracted from the first input is fed into the second layer, and the next input is taken. Again, it is processed and it is passed on to the next recurrent unit. Next input is taken, and this is how it goes on. You cannot just simply feed in one input. You should have a sequence of inputs that is fed, and the recurrent connections will take care of extracting features from the hidden layer. So there are no features from the sequence. So there are two types of recurrent. I mean, there are different kinds of specialized recurrent units. One is LSTM, one is GRU, gated recurrent unit. Then you do have something called bidirectional GRU and bidirectional LSTM. Even more concepts have come up later. But what I'm trying to say is there are situations where you have to just classify as action or classify as positive or negative comment, as we saw with the examples. But there are also other scenarios where you have to generate a sequence itself. When you input a sequence, you have to generate a sequence. For example, here the movie was boring and long. If you're trying to translate this into some other language, there the sequence has to be converted to another sequence, right? So that is also a task of recurrent neural network, sequence generation. That is what is shown here. It's not just a single output. You can see that the sequence of output is also generated. That also that there are tasks that can be, these kinds of tasks can also be covered by recurrent neural network. Okay, there are other specialized architectures which I am not going into I mean, not speaking of now. I feel like you might be already overloaded, and decision tree is also pending. So I wish to cover the coding aspect of decision tree. But there are other, just keep in mind there are other specialized architecture which I don't think it's part of your syllabus. So I'm just stopping here. We'll just quickly, maybe when if required, I'll just go through. Should we have a quick recap? We spoke about the normal neural network, convolution neural network, and recurrent neural network. Did you get a basic idea, basic difference of these three architectures? Okay. Did you get an idea on what the terminology associated with neural networks are? Like, what are the activation functions? What is gradient descent, back propagation, forward propagation, weights, chain rule, how weights are updated? I hope the surface level I could cover, I think. Then, so shall we move ahead with the implementation part of decision tree? I've taken a simple example. I'm not sure if that is enough, but I'll share that collab also with you so that you can try it out or change the data set and try it out for yourself. So I'll just stop presenting with this.
Yes, ma'am. Sure.
Okay. With that, with that, I'll wind up with the decision tree implementation.
Okay. So far, the concepts were clear, ma'am.
Okay, thank you. Thanks for me. I don't think like to the deeper extent you may not have understood, but that is fine because you are listening it. Maybe if those who are listening it for the first time, it might be a bit complex to understand. But listening it for the
we could get somewhat the surface level idea and the concept. What are the factors, terminologies, all those things we understood, ma'am.
Okay, fine. So I'll just tell you. I'll just show the main concepts in the implementation aspects. So I hope scikit-learn. Any hands-on sessions were already covered yesterday or day before?
No, ma'am, not yet.
It started yesterday.
Tomorrow is the first day of hands-on.
Okay, fine. So basic, I mean, more features on how to start a hands-on and details will probably be covered in the tomorrow session. For hands-on, it's better to start offline. I didn't actually prefer having a hands-on session online, but still.
Yes, ma'am.
Yeah, that's what. But then decision tree was not covered, so then she simply shouldn't waste time on that. No, that's why I thought of taking that hands-on part also. So just even if you don't understand, if at all any doubts come up, you can ask me. I'll just share this notebook file. After tomorrow's session, I feel you might be more clear on to how this is
Yes, ma'am.
As of
now, the hands-on session, it will be clear.
Okay,
So
because you're
this
not
would
doing
help us.
alongside me, so you may not understand right now, or you may not have the clear-cut doubts what to ask now. Tomorrow, after having the proper hands-on session, you might get doubts. So if, at that point of time, also, if you want to contact, that's fine. You can ask me.
Yeah, ma'am, sure. But even then, we'll get somewhat picture how it is going
Yeah, yeah,
after
that's
the
good.
session, we guess.
And one more thing is that since Python has all the packages and libraries for supporting the ML algorithms, you need not worry about the implementation aspects. Decision tree or whatever algorithm we are using, most are just direct function calls. Just you need to learn how to load the data set and apply the pre-processing steps and apply the just call the function. How to call the function is just the only thing that you may have to learn, and how to evaluate it. So it's not that complex. As we learned the concepts, it's not that difficult to implement it actually. Okay. So can I take it for granted that all of you are familiar with Python, or
All of you kindly respond. Majority is familiar with Python, I guess, ma'am.
okay, fine. So then what I'm using is a collab interface, a Google
Ah,
collab interface. I think you can see the screen. So
yes, ma'am, it's visible.
what I was given was the lab schedule, in which they had mentioned that in decision tree the question was a retail data set, an online retail data set, and they were I mean it was asked to apply decision tree algorithm onto it and just visualize it, how to evaluate it. That was what the question was. So what I have done is we have imported a set of packages. So as we say always, import cannot be done by heart. Like whenever you want to use a function, you come back and import whatever is required, so need not bother that part now. We'll learn how the functionalities work and then come back. Okay. So one important thing here is a decision tree classifier, which definitely you have to import. That is the function that we are going to use. The takeaway is that it is being given, provided by the scikit-learn package in Python. Under scikit-learn, under the tree package, you have the decision tree classifier. And for visualizing the decision tree, you have the export text and plot tree functionalities, that is again provided by the scikit-learn package. This is what is the important concept that may be newly included as part of decision tree. Otherwise, the remaining label, encoder, classification report, all these will be covered when the proper hands-on session takes place. All these are evaluation parts that are again provided by sklearn evaluation metrics package for evaluating how the model is performing. Evaluation you might have learned yesterday, the concepts you might have learned yesterday, how to perform it with Python. You have direct function calls. You just have to pass on the predicted values. So for that, we have certain functionalities. Those are imported here. Okay. So we'll just move on. Mm, all these are just print statements. What I've done is, when I searched for an online retail dataset, direct publicly available datasets I couldn't find. One was available in Kaggle, but that is not downloadable now. Downloadable now. So then what I did was I searched in GPT. Made use of AI tools, and what we have done is we have created an online retail dataset. That is also fine. When you want to try out with some concepts, you can use generated datasets. So this dataset is actually generated with the structure followed in the online retail dataset that was available in Kaggle. So there was a retail dataset available previously in Kaggle. There you had this recency, frequency, monetary value, average basket size, number, numerical returns. These were there. So I'll just explain what those are. Those variables are. Recency indicates when was the last purchase done. So if it is one, it means that it was purchased yesterday. That particular customer purchased yesterday. If it is 364, it means it is 1 year back. So that is what recency indicate. Then we have frequency as the second feature. You can see that it is some random values between 1 to 50. All these are random values that are generated to create such a data set. It's not an actual data set. So even if you have an actual data set, you can directly read it using read.csv function, which ma'am might teach tomorrow. The same thing will be followed after this step. The only step that you have to skip is this one. From DF, it will be the same. Okay. So this frequency feature indicates how frequently the customer is buying things. So again, that is 1 to 50, or how many number of purchases the customer has made, that is what is indicated by frequency. Then we have the monetary value. Monetary value is from 10 to 5,000, which means what is the amount spent by the customer. So that is again in the range of 10 to 5,000. So you have certain set of values that comes there. Average basket size is 1 to 20, which means that that is a range set, which means that how many number of items are bought in a transaction. Then there is something called number of returned. How many number of products are returned? That is what is num returns that shows. Then we have the final row, that is a target variable, that is also created. The target variable is also created, that and that is appended onto the actual data set. So that is segment, and which segment a particular customer belongs to. We are creating 500 rows in a data set, and for each row we are trying to classify to which segment a particular customer belongs to based on his purchase behavior. Okay, so the segments that we are focusing on are premium, regular, and occasional. Premium customer, regular customer, and occasional customer based on these features. That is what we are trying to create. Such a data set will be created, and that will be considered as the online retail data set. And we are trying to create a decision tree algorithm applied onto this particular data set. So I'll just show you the output wherein the data set is, let me see, the data set is, yeah, this is the data set printed. Recency, frequency, monetary value, average basket size, number of returns, and segments. This looks like a normal tabular data structure. Only thing is that we have generated it. And we are just printing the first 5 rows. It actually has 500 rows. It's a data set of 500 rows. The final column has just 3 sets of values, regular, occasional, and premium. So you can relate it to the decision tree that we have learned. Now, one difference is that the decision tree algorithm that we have learned is ID3, right? Then itself, I told that we have modified algorithms called CART, which will help us handle numerical values. So although the decision tree function that we are going to use here is similar to ID3, the concept that is being used behind the scenes is that of CART. That is why we are able to provide numerical values to these features. Okay, CART has an inbuilt thresholding algorithm that will help convert these numerical values into categorical values. So CART is the actual implementation part of the decision tree used here. Just for your information, because numerical values are also there, so you might think that how it is functioning. Okay, so here we had reached till the segment part. We have created the entire data set here, and that data set is being printed. That is what is done using df.head. Then we are using a label encoder. Label encoder is to encode the target variables, which means that you have 3 classes here. Label encoding is done. That is also a common step. It's not just specific to decision tree. That is common to any classification problem. In label encoder, what is being done is you encode the output variables not just as the string values that is given now, occasional, regular, and premium. Instead, it will be encoded into 0, 1, 2. 3 classes are there, so 3 values will be given. Then only the model will be able to uniformly learn from each of these classes. So label encoding is also an important task before performing the training part. Then we have the train test split. Was that taught to you as part of any step yesterday? Train test split. When you get a data set, you won't be directly using the entire data set for training. You set aside a 20% data set for testing, so that once the model is trained, you have some set of data to evaluate the performance of the model. Okay, so that is a general step. Again, this is also not specific to decision tree. Train test split is something that you will have to do for any ML algorithm. So you split the data set. This test size equal to 0.2 indicates that 20% of the data set is set aside for. So within 500, 20% of records will be set aside for testing purpose. Okay. Then we have the print of train and test size that is fine. So this is the most important function called, which is the decision tree classifier. You can see that the decision tree classifier is called. Here we have created a handle. That means decision tree classifier is the function called or the class that we are creating with a handle DT model. This name can be anything. It's just a handle for fitting the algorithm onto the data set. So decision tree classifier we are calling here, and you can see that there are certain set of arguments in this function call, you can see that there are certain set of arguments. The first argument is the criterion based on which you have to split the tree. Here you are mentioning that it is entropy, which means that you are aligning this algorithm with ID3, the one that we have learned now. So when you choose enter, there are another options which is called the Gini impurity index and all that comes in the CART algorithm. So you can mention entropy here so that it will behave like ID3, although numerical values are also allowed as the backend running is actually CART algorithm. So criterion you can set as entropy so that whatever you're teaching as part of ID3 is actually being implemented here. The only thing is that numerical values will be accepted. Then we have something called max depth. So if we have hundreds of records, it's not like the example that we saw. You will have more and more splitting nodes. You will have a long, deeper tree. There are chances that you get deeper tree. So you can ensure that we just require a tree which has a depth of 4. So what is the maximum depth that is required? That can be indicated there. Then there are two more important arguments there: min sample split and min sample leaf. What is indicated using min sample split is that at least 10 samples are needed before considering that particular node for the split. Okay, if hundreds of records are there and if you're trying to split a node, you should you should make sure that at least 10 records are there before deciding that you're going to split that node. If only 10 records are there, you can stop there. That is what that min sample split indicates. Again, min sample leaf is there, which means that after splitting, if you have less than 5, the value 5 here indicates that if after splitting, if you have less than 5 values for a particular leaf, that may be discarded, that may not be considered. These are not mandatory values. Generally, when you call decision tree, we just set the criterion. We don't have to set these specifically, but just for your know-how that these many arguments are there, I'm just indicating that here. Then we have something called the random state. Random state will, it's a kind of confusing thing for many people. When we start the training of a data set, there should be a random value that we start with, so that every time you run this, you get the same value. So that randomness seed value we are setting to 42. 42, it's being said that it is a golden number. It's nothing like that. You can try with any other number, but when you keep running, you should get the same value. That is why we are setting the random state to 42. Again, that is something that you can ignore, no issues. Okay. So DT model is the handle that we have created for the decision tree classifier. You call the fit function. Only when you call this fit, this is just an initialization. As we create, when you define a class, you will be creating a object, right? That is how this functions. You have not actually created it, or you are not actually trained it. Now DT model.fit function should be called, and the train and the outcome variable, those two variables have to be passed in, train and outcome variable. You can see that during this train test split, you have saved the split data into xtrain, xtest, ytrain and ytest, of which xtrain and ytrain are something that we require for training. Xtest and ytest are required for evaluation. Okay, so decision tree classifier is the only thing that is specific to decision tree. This model fit, and until the train test split part, it is common to any ML algorithm. If you want to fit in linear regression, instead of decision tree classifier, you will be calling linear regression here, and accordingly the arguments will change. Again, you have to call the dot fit function, pass in xtrain and ytrain, and the model will be trained. Once the model is trained, you have to take the prediction for this model with the test values, compare the test value with the predicted values, and see how the model is performing. And you can use the classification report function, which will give you the confusion metrics, accuracy, precision, recall, because this is the classification that we are performing. For that, I'll just show you the outputs. All the remaining part is just visualizations. All are matplotlib visualization, which I'm not planning to explain, but I'll just show you the outputs. 1 second. This is a decision tree that we have got for that particular data set. You can see that the max depth is 4. Root node is ignored. Depth is 1, 2, 3, and 4. It stops with 4. Decision tree is visualized, and then you can also see a confusion matrix. Let me see. Yeah, confusion matrix was displayed here. you can see that the confusion matrix, it's of high accuracy. This is because it's a randomly generated data set, so need not rely on, this is not the confusion matrix, sorry, it's the precision recall F1 score values that we have got. You have a confusion matrix here, 37, 26, and 37 records for each of the class, and the diagonal elements are the true values. So you have got a high result because it's just a randomly generated data set. You cannot reliably say that this is the exactly correct values, and the test set is just 20%, and so it might be just coming around 30, 40, 50. Some 100 records are only coming for the testing purpose. So we cannot reliably say that this is a very perfectly working model and the data set is also generated, but this is how the results look like. Okay, so the only thing that's is different from other ML algorithms is the decision tree classifier function call and the arguments that I explained. The remaining things will be repeatedly told for every ML algorithm when the actual offline hands-on sessions take place. Okay. So with that, shall I wind up? I'll share this Colab file with you so that
yes, ma'am,
make
sure.
modifications as and when required. So thank you all for patient listening. I feel like it has been a little bit overloaded session, especially in the afternoon when, I mean, you cannot take new concepts much, but still that was my task bound to be. So thank you all for patient listening and for the feedback. Every prompt feedback, it actually mattered. Thank you.
Okay, ma'am. Thank you so much. Actually, this session was really interesting, ma'am. And about the last session, at least we could, as it for the very first time, we could see that how it is working and how that decision tree and all those things are getting generated. So it was really informative and helpful for us, ma'am. Thank you so much. And on behalf of all the participants and Department of Computer Science and Engineering, I extend heartfelt thanks to you, ma'am. So thank you so much for the wonderful session. Then tomorrow we are having the hands-on session by Jisha ma'am, Dr. Jisha Mariam John. So the participants all will be coming to our college for the hands-on. Most of the participants will be coming, I guess. Try to come because as it's a hands-on session, only we attend the session under the expertise members, delegates, we'll be able to know how it is working and how things are going on. So thank you everyone for your patient listening. Thank you once again, ma'am, for the session, for the entire session from morning till this time. Already the time is over.
Yes.
So thank you for your dedication and thank you so much.
Thank you. Thank you for the opportunity also. Thank you, ma'am. Thank you all.
Thank you all. So with that, let's wind up today's session. So let's see you tomorrow. And as usual, tomorrow's session will begin by 9:30. So please be on time. Thank you all.